Temperature and time are crucial factors in the curing process, affecting composite quality. Moreover, the curing cycle for an industry-accepted composite typically takes several hours. This limits the production rate. To overcome this, many procedures aim for rapid curing at higher temperatures to shorten the curing time. Do you think this approach is correct? The issue arises from the rapid curing process at high temperatures, which causes internal stress within the composite layers and reduces its quality. Thus, understanding how rapid curing affects composite properties is crucial for production and results in the careful design of the curing process. In this regard, process optimization becomes crucial in balancing quality and curing speed. However, experimental optimization is costly and not very beneficial. So, what is the solution? Yes, numerical simulation as a cost-effective tool has become an essential research method for optimizing the curing process in recent years. In the numerical simulation of curing process, the degree of cure is a key parameter upon which we rely. This parameter indicates the extent to which the resin has undergone curing. It ranges from 0, indicating no curing, to 1, indicating complete curing. However, determining the degree of cure is challenging because it depends on the heat distribution within the material during the curing process. The challenge occurs because there are two sources of heat in the composite: the heat from the surrounding and internal heat generated within the material due to the chemical reactions in the resin caused by curing. In this scenario, the total strain will be affected by multiple factors such as mechanical strains, thermal strains, and cure shrinkage strains. While thermal strains are influenced by the degree of cure in addition to external heat, this forces us to address a complex problem that couples mechanical and temperature fields. In this lesson, our focus is on studying the curing degree and the heat generated within resin due to chemical reactions. We will not explore the mechanical field parameters. Our goal is to help you learn to use the head-wall subroutine for the curing process, which cannot be simulated solely using the abacus. Now let us proceed by introducing the models designed specifically for simulating the curing process in fiber-reinforced composites. To evaluate the heat distribution in composites in curing, we require a thermomechanical model that combines the heat conduction equation with the cure kinetic equation. The cure kinetic equation describes how the chemical reaction of curing progresses. To propose such a model, we should consider both the Fourier heat conduction law and the energy balance equation. The Fourier heat conduction law describes how heat flows through a material, while the energy balance equation ensures that energy is conserved. This way, we have a thermochemical model that predicts the behavior of a system involving heat transfer and chemical reactions. The equation looks like this. Here we have rho for density, Cp for a specific heat capacity, capital T for temperature, and lowercase t for time. But what do Kx, Ky, and Kz stand for? They represent thermal conductivity in the x, y, and z directions respectively. Thermal conductivity is a measure of the ability of the material to conduct heat. However, one parameter that might be unfamiliar to most of you is Q, the so-called reaction exotherm. In this lesson, Q is a crucial parameter that shows the impact of an internal heat source on heat distribution.